Yes, hello friends. So this is the video tutorial for today's GFG problem today, which is quite an interesting one. It's kth missing positive number in a sorted array. And yeah, the question should be in a distinct sorted array because if the array is not distinct, then the question cannot be solved in the time complexity that is expected. So let's read through the question first. It says given a sorted array of distinct positive integers ARR, you need to find the kth positive number that is missing from the array. So let's use this test case. Where is I might have closed it. Give me 1 second. Why is this not? Okay. So here, this is an array, and the assumptions that we are going to take is that this array would be given in a sorted manner, and all the values are distinct. So, like here, if there is a two, there is not another two. Either the value occurs 0 times or they occur 1 times. So, okay, that's fine. Now we want to find the fifth missing value in this array. So, what are the missing values in this array? One is missing because see, all the missing values are said to be positive values. So values would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? These are all the positive values and so on. Dot, dot, dot. Now 2 is in this array, so that it is not missing. 3 is also in this array, so it is not missing. 4 is also in this array, so it is not missing. 7 is also in this array, that it is not missing. And 11 is also in this array, it is not missing. Now we want a fifth missing value. So this is the first missing value, this is the second missing value, third missing value, fourth missing value, and fifth missing value. So the answer here is 9. Okay. So your answer is 9, and yeah, you can also see that the final answer output is also 9. Okay, that is fine. So one way, like we already saw how we can solve this, is basically let's create. So at max, 1 second. Sorry, I'm a bit sick. Okay, so the maximum answer could be k plus n, right? Because see, if all the values from 1 to n are possible in the array, so then the answer would be k plus n, right? So the final answer is k plus n. One approach is that we can create an array from 1 to k, which is well, 1 to k plus n, a Boolean array. And then for each of the values, we'll mark it that if it is in this array, then we will traverse this array of this k plus n size and then find the value that is missing. Okay, that is one approach that we can do. What would be the time complexity of this approach? O of k plus n. Now, if we look at the constraints, I think this would work. Yeah, because k is 10 is to the power n and n is also 10 is to the power 5. But this is not the best way, and this is also not the expected way. Because if we look at the expected time complexity, is O of log n, not even O of n, and we are using O of k plus n. And what if k was like a very big value? It was 10, 1e9, something like that, 10 is to the power 9, then this approach will also fail. Okay, so this is uh, not the best optimal way. So how can we get to the optimal way? Now, there were two constraints on the array that were given, that the array is sorted and the array is distinct, right? Did we use this in this approach? We did not use these factors in this approach, right? We just traversed through the array. If the array was like a random array and it had multiple values, then also the solution would have worked. But let's try to use this value, use these constraints on the array. Okay, how can we use this? Now, can I say that for a missing value x, for a missing value x, what is the like here, let's say for this 6 missing value, which missing value it is in this array, or rather, which missing value is basically like this is the first missing value, this is the second missing value, this is the third missing value, right? So for any missing value x, what position of the missing value it is, because see, we want the kth missing value, right? So if we have a formula for the missing value to convert it back to the its position of the missing value, this could be very helpful for us. So I think the formula would be x minus I plus 1, where I is the index of values before it. So my formula is this x minus I plus 1, and this has to be equal to k because we want the kth value. Okay. What I mean by I is, let me show you. So for this array, 2, 3, 4, 7, 11, let's take this array, right? 2, 3, 4, 7, 11. And let's just also take this 6 case, right? So 6, how many values are before 6? So there's one value before it, there's two value before it, there's three values before it. So the position of 6 would be 6 minus 3, which makes sense. 6 minus 3 equals to 3, and this is the third missing value, and it makes sense, right? Because see, all of the values are distinct and they are sorted, so all of the values before 6 in this array are basically like if we wanted to insert 6, 6 would get inserted at this position, right? So all the values before 6, or less than 6, we can even say. All the values less than 6, number of values that are less than 6, those all are, and those all will occur before it, and as they are all distinct, all of these will not be missing. So the missing value would be 6 minus I plus 1. Why we are doing plus 1 is because see, this is for number of values, we have to do plus 1 because index is 1 base, right? 0, 1, 2, and we have to convert it into 1 base. Okay. So from this, we know that x minus I plus 1 equals to k. So can I say x equals to k, uh, k plus 1 plus I? Now, so let k be, so all of these values. Now, k is given to us, 1 is a constant, and I is the only variable for us. So for each I, if we calculated x and see if this x is valid, then we can get our answer. What I mean by this is see, what are the positions on this array that the missing value could be? So it could be 2, 3, 4, 7, 11. Now the missing value could be here, that is before the array, so it could be like 1, right? This one is before the array. It could be between 2 and 3. Now, in this case, there is no value between 2 and 3, but like if it was 2 and 5, it was 2 and 5, then it could be between 2 and 5, it could be between 3 and 4, it could be between 4 and 7, it could be between 7 and 11, and it could be after 11, right? Now, okay. So let's just say that, so it could be that it is after this index, it could be after this index, it could be after this index, right? Missing value can be after any of these indexes. And we know that if the missing value is after this index I, then our x has to be k plus 1 plus I. Right? We saw this. Now, one way is that again we do a linear search on this array. We find for each index, we find this x value and see if this x value is valid. When will we say that this x value is valid? Is that for this x, it has to be that this x has to be between these values, right? So it has to be that x is between ai to ai plus 1. Right? Then only we'll say that this x value is missing, which makes sense, right? Because if we wanted to find the third missing value, which we know was 6 because we saw that, and we say that, okay, let us find it after the 0th index, then we'll say that, okay, x is 3, but cannot be 3 because 0, yeah, we want to find the third missing value. So it would be 3 plus 1 plus I, so it would be actually 4, right? Now this 4 is not valid because this has to be in between these range. And 4 is also in this array, but that is another thing. But it has to be in this range. Because for it to be after I, it has to be between I. It has to be greater than I, and it has to be less than I. So we'll say, okay, it is not valid here. Then we'll find here. Then we'll go to the first index, then we'll find the value. For first index, it would be 5. So for 5 also, it won't be valid. For 4, we'll do this. So for 4, it would be 3 plus 1 plus 2, right? So this would be 6. And for 6, it is between 4 and 7. So 6 is the final answer. So before, we saw one way linear searching on this, but linear search will again give you a time complexity of n. It's a bit better because we have come from n plus k to n. Why this is better? Because now we can actually deal with if k was 10 is to 9, right? If n or k was 10 is to 9, the time complexity would still be O of n, and our solution would still work. But we can do better. We can use log n. Why we can do log n is see, rather than doing a binary search on this, we can do rather than doing a linear search on this, we can do binary search on this. So will do binary search on the index from index equals to -1 to n minus 1. Why -1 is because -1 is basically this index, this range. We'll say that there's an element at -1. We can say that this element is like negative infinity, like with nothing basically. And we'll say that, okay, if it is after it, so if it is after -1 also, because minus this range is after -1, This range is after 0. This range is after 1. This range is after 2. This range is after 3. This range is after 4. That makes sense. So we'll have to do -1 also. Okay. So we'll do a binary search on -1 to n minus 1. Now for every range, for every index, let's say for this index, we'll find x. Now there could be two cases. One case is that this is valid. So if it is valid, we saw that x has to be between this am and am plus 1, right? Which is fine. The second case that could happen is that it is invalid. And if it is invalid, then also there's two cases. So one case is that x is greater than am plus 1, or rather x is even greater than equals to am plus 1. If this is the case, right? So x is basically, if this is am to am plus 1, x is around here. So if x is here, we have to increase our I. We have to increase our I. So we'll do L equals to m plus 1. Basically, we'll say that, okay, every index before it, okay, sorry. Every index before m will not give me an answer. The index has to be after m, right? Which makes sense, and I will also show you why. Now the other case is that x is less than equals to am. If x is less than equals to am, we'll do r equals to n minus 1. We'll do r equals to n minus 1, and let me show you why. So our final thing would be that when we are at a valid index, this would give you the answer. We'll basically break from the linear search. Okay. So let's use this case only 2, 3, 4, 7, 11. 2, 3, 4, 7, 11. We know our formula for x is I plus 1 plus k, and we know that k is 3. We are finding for the search. So I plus 4, this would k is 3. We are finding for the third missing element, right? So let us see the pattern of this. So if we we'll search for all of these index, right? From -1 to n minus 1. -1, 0, 1, 2, 3, 4. So at -1, uh, our k would be 3. Now, okay, let us write x here. It would be 3. Now at this it would be 4. At this it would be 5. At this it would be 6, 7, 6, 7. Sorry, 6, 7, 8, right? Now, see, 3 is not in this range because it is very much bigger than the next value. So our answer has to be in this part. Right? Now, similarly for 4 also, it has to be in this part because it is greater than its next value. For 5, it has to be less than this value, and C6 is valid. Now, for values that are after the answer, the value would be less than AM only, less than equals to AM only. We can see here that this X is less than equals to AM, and this 8 is also less than equals to AM. So if X is less than equals to the mid value, then we'll say that the answer is before it. If X is greater than equals to the next value, then we'll say that the answer is after it. And which makes sense, right? Because see, what we want is that this X has to be between AM plus 1 or AM plus 1 and AM. Now, if X is very big, if X is very big, right? If X is very big, then our answer, our AM will have to also increase, right? This value has also, this value also has to increase. So we'll have to say that the answer is after it. And if X is very small, then we'll have to say that, okay, we'll have to decrease our AM to meet its value. That is why we'll say that the answer is before it. Let me show you the code. I think I've over-explained it a bit, but that is fine. Okay. So in N, we'll basically say store the size of the array. And L, as we saw that the answer can be between -1 to n minus 1. And I would be the final breaking index, and we'll store it into I. So finally, we can return k plus I plus 1 because we saw that, okay, this ith index will gives me a valid x, and for this valid x, this I, the missing value would be k plus 1 plus I. Finally, for each range, we'll calculate the mid. We'll calculate the x, and we'll see if this x is valid. And as we saw, the formula for it is k plus 1 plus n. Now, There could be two cases. One case is that m is minus 1. If m is minus 1, we do not need to check this case because we'll actually say that at minus 1, the value is negative infinity. So x can never be less than this. But if f is not equals to minus 1 and x is less than equals to mid value, then we, as we saw, well, the answer has to be before it. So we'll do r equals to n minus 1. Else, so else is basically that x is greater than ARR of n, which is great for us. Now we'll have to do one thing, two things. We'll need to check that if x is less than ARR n plus 1 also, then we'll see that, okay, this is valid. So I equals to m and we'll break here. So how can we do that? So one thing that we will again have to see if that n plus 1 is a valid index, because if it is not a valid index, then then the last value of the array will can say it is positive infinity. So x would always be like less than positive infinity, or it is that it is a valid range, right? So yes, that makes sense. So if this is the case, we'll just set I equals to m and break because we have found our valid index. Else is that x is greater than ARR of m plus 1, then L has to be m plus 1. Then the answer has to be after it, so L equals to m plus 1. Yeah. So this works. The time complexity is of log n as we are doing a linear search or a binary search on n values. And yeah, we are not using any space. Yeah. Thank you for watching. If you were able to understand anything, give me a like and subscribe. All of those things. Bye.